a carbon-carbon double bond has a carbon that is electron deficient. Because if I put other carbon groups around it, that seems to stabilize the situation. Now, all experimental evidence is that it doesn't make as big a difference with alkenes as it does with carbocations. But you have to understand that a carbocation is much more desperate than an alkene. The alkene carbons don't have a formal charge of +1. I'm just suggesting that maybe they have a slightly negative, and slightly positive character. So, same disease, but a less serious case. Now, why might you argue that a double bond carbon is slightly electron deficient? If we look at the orbital system, it looks like this. Is there anything in that structure of the orbitals that would possibly explain why a double bond carbon is slightly electron deficient? Think simply, is there something unusual about this carbon, say as opposed to methane or ethane? Pi bond. Pi bond should make you suspicious as the cause of this problem. What's not so good about a pi bond in terms of getting electrons to that carbon? What? Yes. What makes a pi bond weaker than a sigma bond is that it takes the electrons away from the nucleus, and it's made up of two p orbitals, and what happens at the center of the p orbital, where the carbon is? What about the electron density right there in the middle of the figure 8? It's 0. A pi bond has virtually no electron density directly where the carbon nuclei are. So a pi bond is really poor at making sure the carbon gets its fair share of electrons. Yes, there are 2 electrons in that pi bond, and some of that belongs to the carbon, but the pi bond's not paying up. It's not showing up with the electron. So double bond carbons are slightly electron deficient. Not as bad as a carbocation, but it's the same problem, helped out by the same structural feature, substitution with alkyl groups as opposed to hydrogens. So that's what's behind this. And this happens to be a reaction where the more stable product is formed faster, and that's why you're getting this more substituted alkene. Now you could actually get a maximum of 3 different alkenes, because if you've got a carbon with the halogen, there are only 3 other carbons that could be attached to it. So you could have, say, CH3, CH2, CH3, CH, an isopropyl group here. So there you see the maximum confusion, where if you need to lose H and X off 2 adjacent carbons, it's not just A and B, it's A and B and C. You could lose HX this way, let's call that A. You could lose HX this way, or you could lose HX that way. And all that would happen is you would pluck out the H and the X and just paint in a pi bond. So make a double bond where you used to have a single bond. Make sure you take out the H and the X. So one of the alkenes would have a double bond to a CH2 here. This one would have a double bond to a CH3. This would have a double bond to a CH3. Oops, this should be C. So of the three, A, B, and C, what would be the major product? C. C is going to give you the most substitution on the carbon-carbon double bond. And so C would be the major product, and you would just, when you write the structures for A and B, you would just label them both as minor. Now, you could add up that the minor products in total are larger than the amount of A, so this is kind of a messy situation here. Probably not a good scenario for a reaction, but that's what you would predict would happen. And there's also this business of statistics. If you have to remove a hydrogen, isn't it better to have more hydrogens where you want to remove one than less? So if you've got a base that's trying to remove a hydrogen, there are 3 hydrogens of the A type, 2 of the B type, and only 1 of the C type. So there's a statistical problem here where C would form the major product, but it's going to have a problem because the A hydrogens are 3 times more prevalent than the C hydrogen. So this is a complicated scenario. And to make it even more complicated, these things tend to be reversible. So all of this can kind of stew around back and forth, and who knows what's going to happen at the end. The truth of the matter is you can predict the outcome of all of the reactions that you want to, but until you get up out of your chair, go into the lab and run the reaction, you'll never be sure. Unless somebody else has run it before and you can see the result. Chemistry remains an experimental science. Even with the largest supercomputers that we have, and the United States now, you may have read, has 3 of the largest supercomputers in the world, they are incapable of mathematically predicting the results of these reactions. Even though all the mathematics necessary to do that are known. We know the equations, they're just too complicated for even a supercomputer to solve. At some point, we may be able to be more theoretical, but it's still totally experimental at this point. Okay, let's see. Well, I think that's about it. Just to remind you, when you get a reaction, let's say like this.
I missed what he just erased. Ronnie, can I see what he just erased? I missed that. Because I was...
Thanks. What the KOH is? Or is it another?
No, that's the solvent of the reaction.
C major.
It's common to list a
It's easier.
solvent if it has some consequence in the reaction. So not just any solvent, but the fact that I'm specifying ethanol is supposed to give you a clue of the expectation. And a combination of KOH, ethanol, and heat, all 3 of them, the expectation is elimination. If you don't see all 3 of those, it's automatically substitution as the expectation. So it's not difficult. But you take an example like this, and this goes to what you're saying. with ethanol or alcohol with heating. That's elimination. So here's your alkyl halide. Now you have to be careful, this is a line drawing. And you have to eliminate H and Br. So you want to draw in the hydrogens on any carbons that are next to the Br. And you can
What
see
over what? Okay, wait.
there are two different types of hydrogen.
What's
This
in
is a
parentheses?
CH2, but I
Alcohol.
only need one of the hydrogens. So I can lose HBr from two adjacent carbons that way. But I can also lose
Ooh.
from two adjacent carbons this way.
Shit, leave room. I do
The
that.
rest of the molecule is really just going along for the ride. And be careful about that, because you can get at least part of the answer wrong if you simply fail to carry the rest of the molecule along that has nothing to do with the reaction. Reactions occur at a specific site in the molecule. Everything else just has to be copied. So that's one alkene,
got
and
excited
the other
molecule.
alkene would be this one. I'm also producing HBr, of course, which in KOH ends up as potassium bromide and water, because the KOH certainly will react with the HBr. But you can ignore all of that inorganic stuff going on. Organic chemists care about the organic transformation. Which one of these, the left one or the right one, would be the major product? Right one. This one here has 1, 2, 3 carbon substituents. Now another way of looking at this in terms of how many substituents you have on a double bond is just to notice how many hydrogens are there. More substituents means fewer hydrogens. So that one on the right has 1 hydrogen on the double bond. This one here has 2 hydrogens on the double bond. So the one on the right, therefore, is more substituted. For some people, it seems to be easier to look at the hydrogens. But remember, what you're looking for with the major product is as few hydrogens as possible on the double bond. Nothing else matters. So this would be the major product. And that's the minor product.
Do you want us to show like the fission of the electrons in the reaction?
That's a mechanism. That's a good question. We've studied some mechanisms, in particular the SN2 and the SN1. I still need to say a couple words about the E2 and the E1 also, but if a question says, write a mechanism for a reaction, then you have to use the curved arrows that show how all of the electrons transform. Bonds break, bonds form. Intermediates sometimes appear along the reaction that are known. Any bonds that break, or any pairs of electrons that move, you have to move with a curved arrow. Any intermediates that are known to form in a reaction have to be shown. So if it's a two-step reaction with a carbocation, you'd have to write the carbocation and then use curved arrows for the next last step. Writing a
The next
mechanism
last
is
step.
hard. There's a lot of detail to it. Don't do it unless the question says write a mechanism. If it simply asks what's the expected organic product, don't volunteer a mechanism. And don't try to name the compound if it doesn't ask you to do that. Read the question and do exactly what the question is asking you to do. No more, no less.
Kasner would say,
Now,
"Do
you
what
may
I
be
tell
asked
you
to
to
write a
do."
mechanism, particularly for the SN2 and the SN1, but you can do that. But you have to be careful. It's a story. And it's a story of how the electrons move around in the reaction. And as we start to look at organic reactions, what I want to impress upon you is that the way we look at how all of these reactions occur is simply as a movement of electrons. This is electron pushing, as it's been called. In fact, there are textbooks entitled Electron Pushing in Organic Chemistry that focus on how you write these mechanisms. Nothing ever happens to any of the nuclei. It's just an electronic transformation. It's not nuclear chemistry. Nuclear chemistry does exist, but that's a whole different thing. We're not touching anything in the nuclei. We're just moving electrons, breaking bonds, forming bonds, etc. Now, the E2 mechanism has a tricky aspect to it that you sometimes see in questions, particularly on standardized exams like the American Chemical Society exam.
I like the Chem 2.
When the
That's horrible.
H and the Br, or X, doesn't have to be Br, are lost. So the E2 is your base, let's say it's a hydroxide ion, comes in, snatches a proton off the adjacent carbon, and what you have to picture is sort of a domino effect. As the base pulls the proton away from that carbon on the left, since the hydrogen is pulling away as a proton, the electrons in the CH bond are staying behind. Now, they could just sit there, but what they do instead is they start to morph into a pi bond. That's what that bottom curved arrow is really saying. The CH sigma bond pair is now hanging loose, and as it hangs loose, it morphs into a carbon-carbon pi bond and pushes and breaks the carbon-bromine sigma bond to make room for itself. So again, it's like three dominoes that you tip over. First one knocks the second one knocks the third one. And it's all considered to be one step. That's the E2. E because it's elimination. 2 because it's bimolecular or second order. Remember that 2 refers to the kinetics, not the number of steps. 2 because you can see if this is the whole picture, you need the base and you need the alkyl halide. 1 plus 1 is 2. So the rate depends on both of those species. So it's bimolecular or second order. Now there's another requirement, and that is the hydrogen and the bromine, as it turns out, and we learned this from experiments. Turns out that the hydrogen and bromine have to assume a position where they're trans. Now that carbon-carbon bond between them is not a double bond. So you would not normally talk about cis and trans. We're just talking about a conformation here where the bromine and the hydrogen are on opposite sides of the middle carbons, and they have to be in the same plane, like this. It's called being trans-coplanar. Now, how do we know that this is a requirement? It's because accidentally it's been noted that in a compound that can't assume this position, elimination doesn't occur. Now, there's no need to get into it horribly, but in cyclic alkyl halides with the halogens on a ring, depending upon the other substituents, sometimes there's a hydrogen next to a bromine that can't get trans and coplanar because of the ring geometry and the substituent pattern. It just can't do that. In that case, elimination does not occur. So it's not enough simply to have H and Br on two adjacent carbons. They have to get in the right orientation. This is no problem for any open chain alkyl halide, because you know that single bonds can rotate freely. It's only a problem that occasionally comes up in certain cyclic alkyl halides, just so you know that requirement. Okay, that's about it, I think. Yes. Question? Pardon? Anybody? That's not even a whole molecule. I'm just forming a double bond. So if this, for instance, were say ethyl bromide, see that.
I need some snacks and you're good to go.
And that's the E2. If this had occurred to the E1, you'd simply draw a carbocation first as the rate limiting step. So in the E1 mechanism, the bromine just leaves seemingly on its own, and you get a carbocation. And then the proton leaves afterwards. So you lose H and Br, but the Br goes first, and then the H afterwards. That doesn't have any stereochemical requirements like trans and coplanar. And again, it makes no difference in the nature of the product.
I just want to make sure, so you said the H leaves the electrons?
Well, you kind of have to picture it all happening simultaneously.
And then the electron with it, is that how it works?
Yes, right. Yeah, you see the curved arrow. The head of the arrow shows where the pair of electrons ends up, in this case on the bromine. So when the proton is lost, it leaves sort of an extra pair of electrons behind. And then when the bromide ion leaves, it takes away that pair of electrons. So everything kind of balances out. But it's, you want to see it almost as if you had three springs and you scrunch them all together in your hand and then let go and they all pop. This reaction is popping H and Br off like that, like a jack in the box, and then you have the line. It's one step. Okay. All right, let's stop there, and we're all set. If you have any questions, just email me or stop by. Don't forget, Tuesday, 9 o'clock. Just a 25-point quiz, so that's like double the amount of time it should be.